Let's quickly decode the ASHRAE liquid cooling classifications and what they mean for our infrastructure design. Start at the top with W17 and W27. You'll see the supply temperatures are tight, 17 and 27 degrees Celsius. To hit these targets, the table shows our primary facility is the chiller. We are still reliant on mechanical compression here, which keeps our PUE, power usage effectiveness, higher. The real shift happens at W32. With a 32-degree supply, notice how the primary facility switches to the cooling tower. In most global climates, W32 unlocks full free cooling. The chiller is demoted to a backup role. This is where we see massive energy savings. Finally, look at W40 and W45. At these high temperatures, we eliminate chillers entirely. The focus in the secondary column shifts to district heating. We are no longer just rejecting heat. We are harvesting high-grade heat for reuse. In short, moving down this list means moving away from power consumption and toward energy sustainability. Let's walk through the critical parameters for this liquid cooling unit. First, look at the operating temperature, 17 to 65 degrees Celsius. The key number here is the floor, 17 degrees. Why 17? This is directly tied to ASHRAE guidelines. We must maintain the coolant temperature at least 2 degrees above the dew point to prevent condensation. If we go lower than 17, we risk water forming on the IT equipment, which is a failure condition. For non-operating, the range is massive, -40 to 85 degrees. This isn't for the data hall. This is for logistics. It ensures the unit survives air shipment at high altitudes or storage in extreme heat. Regarding service life, the 10-year rating is calculated based on the pump's failure curve. Finally, check the filtration. We require a standard 200-micron filter for the primary loop, but a much finer 50-micron filter for the secondary loop. This is critical to prevent clogging in the microchannels. So when designing the loop, keep that 17-degree floor and the 50-micron requirement top of mind. Let's focus on the heart of direct liquid cooling, the CDU, liquid-to-liquid coolant distribution unit. As engineers, we define this as the hydraulic separation point. It isolates the rougher facility water system, FWS, from the precise technology cooling system, TCS. Think of the CDU not just as a heat exchanger, but as the brain of the loop. It regulates flow and pressure to protect the cold plates inside the servers. Now let's look at the two form factors. First, the in-rack CDU, shown in figure right. This is a standard rack mount chassis, typically 4U or 5U. It is designed for modularity. It sits directly in the server rack and manages the manifold for that specific rack only. Contrast that with the in-row CDU in figure left. This is a floor standing unit with much higher capacity. It doesn't serve just one rack. It drives the flow for an entire array of racks. It connects to a larger network of manifolds, supporting either top or bottom feed configurations. So the design choice is simple. Use in-rack for granular control, or in-row for high-density cluster scaling. Regarding mechanical design, the priority is rack alignment. The CDU's footprint must mirror standard rack layouts. This ensures we can scale the data center up or down seamlessly without layout conflicts. For operations, we require full serviceability. Access must be available via the front or rear doors. And finally, regulatory compliance isn't an afterthought. It must be integrated throughout the entire product development cycle. On material selection, the rule is strict compatibility. Every component touching the fluid, what we call the wetted materials, must be chemically neutral to the coolant to prevent galvanic corrosion. Don't guess here. Refer directly to the OCP database. They have specific approved lists for both propylene glycol and water-based systems. This is your baseline for safety and environmental compliance. Moving to pump selection, the operational non-negotiable is redundancy. You must design for at least N+1. This ensures continuous flow even during a pump failure or scheduled maintenance. For construction, standard stainless steel 304 or 316 is required, but pay special attention to the mechanical face seals. Specify high-wear materials like silicon carbide or tungsten to prevent early leakage. Finally, regarding cooling loop integration, the metric is simple: a leak-free network for the entire service life. Look at the complexity in figures. There is no room for error. Whether it's the compact in-rack or the large in-row assembly, every tube connection requires precise sealing materials. Do not deviate from the manual. Strict adherence to assembly best practices is the only way to qualify the CDU. On the control side, the CDU tracks the critical triad: pressure, temperature, and flow rate. It doesn't just log data, it watches for deviations to trigger immediate operator alarms. Crucially, we rely on automated safety mechanisms. If a failure occurs, the controller must instantly cut pump power or isolate valves. And for physical protection, the leak sensor rope is the industry standard for containment. Let's talk quality control. The rule here is simple. A CDU is only as good as its weakest valve. The final product quality is heavily dependent on every single subassembly used as a building block. While we integrate QC during design and procurement, this section targets the danger zone, post-production QC. This is the phase most often overlooked, yet it is critical for catching latent defects before deployment. Regarding surface treatment, we have two distinct protocols. For stainless steel parts, passivation is mandatory. You must follow ASTM A380 to chemically create that protective oxide layer. However, for softer metals like brass or bronze, passivation isn't enough. Here, we require electroplating, typically nickel or chrome, to shield the component from environmental corrosion and extend service life. Moving to cleaning, the target is zero FOD, foreign object debris, and oil. A critical caution on air drying. Your compressed air system must be filtered. If you use dirty air to dry parts, you are simply recontaminating them. For machined components, air drying isn't enough. We recommend steam pressure washing or an ultrasonic steam bath. This is the only way to guarantee a pristine finish before final assembly. On fluid servicing, sensors are your first line of defense for levels and leaks. But they don't tell the whole story. You must perform periodic sampling to assess the actual chemical composition. Over time, fluid chemistry drifts. When this happens, you need to intervene with chemical dosing to rebalance the loop. Always follow the fluid vendor's guidelines. Never improvise with the chemistry. Regarding filling and flushing, the golden rule is compatibility. Never introduce a cleaning agent that conflicts with your loop chemistry. Always consult the vendor first. But here's the critical protocol. Regardless of what you clean with, the final flush must be done using the actual operational coolant. This is mandatory to prevent dilution before you go live. Use a dedicated flushing cart to control this process. Regarding filter servicing, consider this your last line of defense. We are filtering to stop solids and FOD from clogging the most sensitive part of the loop, the cold plate microchannels. Proper sizing isn't just about safety. It protects soft O-rings, reduces pumping power, and significantly extends the MTBF, mean time between failure. For dimensions, strict adherence to standards is non-negotiable. Rack mount units must fit EIA 310 or ORV3 frames. You are designing typically for 4U or 5U increments to ensure ease of deployment. In contrast, in-row CDUs operate at the rack scale. These units conform to full cabinet heights, typically 42U or 48U, aligning physically with the IT rows to deliver maximum cooling capacity. Moving to cosmetic inspection, consider this your first line of defense. It goes beyond simple aesthetics. You must execute a complete visual check strictly following the first article inspection, FAI, criteria. Your target is specific. Verify the physical specs and ensure there is absolutely zero hazardous debris or FOD hiding in the unit. If you see manufacturing waste, the unit fails. On structural design, integrity isn't an afterthought. It must be baked into the entire life cycle, from material selection to manufacturing, to withstand shock, vibration, and pressure. Crucially, for data center deployment, you must account for seismic loading. Do not rely on generic installation methods. Follow the manufacturer's manual strictly, or consult the application engineer to ensure earthquake readiness. For assembly and integration, rigidity is just the baseline. The real engineering challenge is smart routing. Your electrical and tubing paths must never obstruct future maintenance access. And for safety, the leak sensor rope cannot be placed randomly. It must strictly trace the coolant flow path. This is the only way to detect and communicate a leak proactively. For performance testing, we strictly divide it into two stages: ingredient level and system level. You verify the individual pump curves and valve ratings first, before qualifying the full assembly. The real challenge is the industry's lack of standardization. To compare apples to apples, ignore the marketing fluff and lock in on these key metrics: cooling capacity, approach temperature, and the specific flow conditions for both FWS and TCS loops. This diagram illustrates the core function of the LLCDU hydraulic separation. On the left, you have the TCS loop collecting heat from the IT stack. On the right, the FWS loop rejects that heat to the facility. Crucially, notice the temperature logic. We must maintain the FWS supply temperature above the dew point. If we run too cold, we risk condensation on the heat exchanger. For low temp operations, a bypass or insulation is mandatory. This graph plots heat load against approach temperature, ATD. Remember the formula: ATD equals TCS supply minus FWS supply. As you can see, the relationship is linear. Engineers, pay attention to the colored lines. Different facility water temperatures result in slightly different performance curves due to fluid property changes. You need to select the curve that matches your facility's specific operating point. Regarding TCS pressure head, the goal is simple. Your CDU pump must overcome the total loop impedance, the DP. You are calculating to beat the pressure loss. Look at figure. This PQ curve shows available pressure versus flow. Notice the gap between the dashed and solid lines? That is the pressure penalty imposed by quick disconnects, QDs. You must factor this loss into your hydraulic budget. Switching to the FWS side, the focus shifts to impedance. Remember, the CDU is a restriction in your loop. Your facility pumps must be powerful enough to push the required flow through this resistance. Look at figure. The solid line shows the pressure drop with quick disconnects. That gap represents significant head loss. If you fail to account for this extra DP in your facility pump sizing, you will starve the CDU. To stop the guessing game, we recommend a standardized capacity rating. The industry golden rule for flow rate is 1.5 LPM per kilowatt. At this flow, your CDU must deliver specific pressure heads to be compliant. For in-rack units, we mandate a minimum 25 psi head. For larger in-row units, that requirement jumps to 40 psi. If you can't maintain these pressures at 1.5 LPM per kilowatt, your capacity claim is invalid. Beyond a single number, we build a capacity matrix. This maps ATD, approach temperature difference, against flow rate variables. This is where design wins happen. If you can optimize your cold plates to run at lower flow rates or achieve a tighter ATD closer to 5 degrees, you are effectively unlocking free cooling capacity from the same CDU hardware. For reliability, ensure all wetted polymers and metals are chemically compatible. Then, respect the filtration hierarchy. We demand fine filtration for the TCS loop, 25 to 50 microns, versus a coarser 150 to 250 on the facility side. Crucially, for operations, the best practice is hot swappability. You must design pumps and filters to be replaced on the fly, ensuring ease of maintenance without shutting down the cooling. For hydrostatic pressure testing, we adhere strictly to IEC 62368-1 and ASME B31. The pass criteria are binary: absolutely no leaks and no physical deformation under pressure. But note the workflow. This isn't just a one-off check. You must perform a pressure verification per ASTME 1003 after every mechanical or thermal test run to ensure the loop integrity remains compromised. On chemical compatibility, the enemy is twofold: galvanic corrosion from dissimilar metals and leaching from reactive polymers. Either one will deplete your inhibitors. Start with a basic coupon test or salt spray, ASTM B117 for a baseline. But for long-term reliability, you must run periodic sampling via ICP-MS. This is the only way to track fluid degradation at the molecular level. For dynamic testing, we rely on two pillars: IEC 60068 for structural integrity against vibration and shock, and ISTA standards to simulate the brutal reality of shipping and handling. Here is the critical workflow. The test isn't over when the shaking stops. You must follow up with a pressure test. We have to verify that the dynamic stress didn't crack a seal or loosen a fitting. Regarding thermal cycling, we simulate the full life cycle. This means validating both the stable operating range and the harsh non-operating shipping conditions, where we use fast ramp rates to really stress the materials. The failure mode here is deformation. Therefore, the protocol is strict. Immediately after cycling, you must execute a pressure test. We need to confirm that all that expansion and contraction didn't crack a seal.